Okay, let's go ahead and get started. Okay, I'll bring up the projector near the end of class. So I'll point out some schedule things. Main thing, just announcement to make is that homework 3 is posted today, due in 2 weeks. And you'll see on the way to do some MCMC sampling methods. The first one is an image example with the Markov framing field and binary images that we kind of saw before. We'll talk about Gibbs sampling this week, which is kind of, we're going to tackle the first one. And then the second one is a simple classification problem. But you're going to solve it through MCMC sampling. So anyway, we'll kind of go over those things a little bit later. Okay, but today we're going to continue talking about Monte Carlo. And so just to remind everybody where we were last time, we're talking about Markov chain, Monte Carlo, MCMC. And the idea is that we want to sample from some distribution, but doing that directly is too difficult. We don't have to directly sample from the distribution. And so instead we sample from a Markov chain of random variables. And so forth. Dot. Easy. Where we know how to sample somehow conditionally xk given the previous xk minus 1. So wherever we are in the chain, we have somehow the conditional distribution to get a sample from the next random variable in the chain. And so that's the thing we know how to sample from. And each of these xk's are not the distribution we want, but the trick in MCMC is going to be to get this chain to converge to what we want. So in a limit, as k goes to infinity, xk is going to converge to the right probability distribution as a random variable. Okay, and along these lines, we were just talking about Markov chains in general. And we had talked about the Markov property, which is basically the usual thing we had talked about before was that this distribution only depends on the previous random variable, and given the previous random variable, we don't need to know anything about the random variables that are before that. Next door neighbor just behind me. And we talked about it needs to be homogeneous, meaning that the conditional distribution of each of these arrows is the same distribution. So you can't change conditional distributions halfway down the stream, so you have to keep that consistent. So those are the two properties for these Markov chains that we were talking about. Homogeneous is on top of the Markov property, right? So this, I just gave you this Markov chain. You could technically define these arrows however you wanted to, but we're going to have one more constraint that is a homogeneous Markov chain. Okay, any questions about that? That's the kind of setup we were at last time. So then we're looking at, we were starting with discrete, and so discrete, we have some set of states, that this can take values. The space is some kind of discrete states, S1, S2, out to whatever. So there's some number of states. We were doing this one example with 3 states, and we had a state transition. And not to be confused with random variable graph, this is a state transition graph where your arrows basically tell you the probability if you're in one state of transitioning to the other state. And I kind of had this one example. There's an example in the Andrew paper of another state transition graph, but this is the one I had from last time. It was just kind of fully connected here with 0.5 on these loops, and I'm going to drive them all in, and then 0.25 on each of these kind of inner edges. And what we said was, I can write this transition graph. This transition graph is the conditional distribution of if I have an x value here, if I'm in some state, because this x value, when I get a realization of this random variable, it's going to be one of these states, in this case S1 to 3, then the probability of x2 popping out as some other state is given by this transition graph. And another way we can write this, we said, was as a matrix, so the transition matrix T, we'll call it. In this case, just 0.5, 0.5, 0.5 on the diagonal, and you have 50% probability of staying where I am, and then everything else is a 25% probability of transitioning to any of the other 2 states. So this is kind of what this graph looks like in matrix form. And one way to see, or probably, of course, this transition probability is really just the same thing as P of xk. Like I said, the conditional distribution P of xk given xk minus 1. It's equivalent, these are equivalent concepts, right? This is just writing the x kind of k as kind of a row here, and xk minus 1 is kind of columns. That, looking that up, gives you these probabilities for, if I were to ask, let's say this is state 1, what's the probability of getting to state 2, I would go with the second column, or sorry, second row and first column. And that's where that probability would be, that initial probability. We'll forget what question we're doing.
So what's the significance of number of states?
There's no, it's just the example. So this is just, it's just a random variable that can take some set of discrete values. That's all. So the states are just, like Bernoulli random variable, we have 2 states, 0, 1. I'm just doing discrete.
States can be the values of random variables.
Yeah, these are the values. So I'm just giving them, names S1 through SD. Yeah, so there's D values. Integers 1, 2, 3, 4, 5 out to D, whatever you want. So yeah, and I'm just doing the finite state machine case because it's easy to get a brain around because it's finite. I can write down all the combinations here in the matrix. That's why I'm doing this, because we're going to see the matrix interpretation will help us think about this. If this was, if this was like, I had like the space of all integers in my outcomes, I couldn't write a matrix because it'd be infinite by infinite matrix. So this is going to help us think about why it works. But of course, this does work if this was an infinite state, infinite set of outcomes from our random variables. And then we're going to also talk about real values, so continuous values, where it's clearly not a matrix. It's not even, you couldn't even write as discrete rows and columns, obviously. So anyway, yeah, this all works. This Markov chain stuff all works no matter what kind of random variables the x's are, but for the simplicity of understanding why it works first, and in the special case of finite discrete values, it'll give us the intuition for why it works in general. So that's a good point to make. Okay, so that was where I think that's kind of where we ended last time. One more thing. So the probability, I'm actually going to use, I think I'm going to just use the notation that this random variable has PMF, P0, this random variable has PMF, P1, and so on. I'm going to put a subscript on the P just to kind of really reinforce the fact that if I say P of x2, it's not the same thing, it's not the same distribution as P of x, if I said P of x1. So I'm going to put a subscript, say P1, P2. These are different probability mass functions. And remember, probability function is really just a d-dimensional vector, right, that has to sum up to 1. It has to be positive, or I should say, greater than or equal to 0 entries in the vector, and it sums up to 1. So it's a probability of each of these states is what each entry in that vector. So it's a probability vector is the way to think of these probability mass functions. And yeah, so
are they given the previous value? So is it like
this is just the marginal. So this is P1 is kind of a function of x1. You think of it's not conditional. This is the conditional, and it's the transition matrix, which is this, and the homogeneous remain fixed. So this conditional, we know for the whole chain is fixed. That's the homogeneous property, yeah.
So in infinity, PM will be like function which we are trying to sample.
So that
probability mass function for the infinite random variable will be same
of
as
infinite random. Yeah, right, exactly. Yeah, so this PMF, this probability mass function, if we said had all integers as outputs, would be you could think it's an infinite vector, but it's the probability mass a geometric distribution, for instance. You can go from 1 to infinity, and that geometric probability mass function would be what we would be talking about here. Yes.
And we are saying at infinity the xm would be like same as
infinity this way.
Yes.
Yeah.
So PM will also converge to the probability function which we are sampling from.
The one that we want to sample from.
Yes.
The goal is
The goal
is that as m goes to infinity, PM will be whatever it is we would like to sample from. Yeah. I mean, here, this is not terribly useful, by the way, for the finite state case. If you're talking about MC. Now, finite state machine Markov chains are useful in general, but if what your goal is to sample from a finite distribution, then it's just a 3 vector in this case, and you can specify that 3 vector, and it's not a big deal. But how these Markov chains work will get us to the case where things might be more complicated, like they're infinite state space or continuous state space, where we have harder time specifying it. That being said, I should be careful. The three cases is, since X was like the space of binary images, that's still finite, but it's exponentially blows up in the number of states you can have for like the space of like large binary images. So I take that back a little bit. It is still interesting. In fact, that's your homework assignment, is to do an NCMC, and it's just a finite thing, but it's impossible to sample directly from. So I take that back a little bit. But the three vector case, clearly you would never do MCMC because you would just specify the 3 probabilities and you would be done. But as we've talked about, for instance, a binary image, if I've got n pixels, there's 2 to the n states. And if n is any kind of reasonable sized image, 2 to the n is huge, and you can't enumerate all the probabilities of all the images. Okay, good. Okay, so yeah, so we're going to use the notation that that kind of this limit as m goes to infinity of this Markov chain is going to be look like that Pm is going to be converged to some probability I'm going to call pi, some probability vector case in the finite case, but this could be a probability density function in the continuous case. But we're just going to say that what this thing is going to converge to is some probability distribution pi. Okay? And the first question is, well, am I really guaranteed? Let's forget about that. I'm actually trying to target a specific probability distribution here. Let's just say I give you a Markov chain. I give you this transition probability. Okay? Am I really even guaranteed that it's going to converge to anything? How do I know it doesn't just transition back and forth, for instance, between one probability distribution to another? P0 is the same thing. P's are different. How do I know that doesn't happen? How do I know I'm really going to converge to something stable? So it turns out that there are there's two conditions that we're going to need. So conditions for this to work out. The first one is called irreducibility. And irreducibility means that I can get to all states. From any state to any other state, basically. So if I start you in any state in this graph, there's some non-zero probability with at least a few jumps. At least it might take multiple steps, but at least with some non-zero probability, I can get to any other state. So clearly, this one satisfies irreducibility because I can get to any other state in just one jump. It's so another way to irreducibility is that this state graph is fully connected, right? Not fully connected, but it's connected, right? There's some path between any two states. That's one way to think of it. Okay, and notice, of course, here the edges are always directed, so you have to kind of follow in the direction of the arrows. It has to be kind of connected with respect to. You can't have a state that just has arrows going into it and then no arrows going out of it, because then that would you couldn't go from that state to any other state, right? So the edges, the directionality matters here. So that's irreducibility. And then the second condition that we're going to need is aperiodicity. So this just means that it doesn't get stuck in cycles. It doesn't mean that we can't have a cycle in this graph. So this graph has cycles, but there aren't forced cycles. So you're not forced to go I can bounce around and change directions in this graph. If I had, let's say, but it was something that looked like this, then I'm forced to be in this cycle. Okay, and I mean this one's very uninteresting because if I just have this only one edge coming out of each each variable here, it's going to be probably 1 because that's the only thing I can go in. So that's not terribly interesting, but anyway, the point is anything where you have places where you would get trapped in the loop that you couldn't get out of, that would be a periodic transition system, and with that. And I'll show an example in code here of a Markov chain that violates this, and we'll see that it doesn't converge to. We'll see why it breaks the thing here. Okay. So if I have these two conditions, and I have a valid and this is an honest to goodness conditional probability. So this has to be a conditional probability. I can't just throw in arbitrary numbers here that don't represent a conditional probability matrix here like this. But if I conditional probabilities and their kind of state transition satisfy these two properties, then I'm guaranteed that this is going to converge to a stable distribution. Okay. And this is called the stationary distribution. We'll see in a minute why it's called stationary distribution. But basically, it means that if you were to ever actually get the p vector equal to this pi, then it's stable. It's stationary because it doesn't change. The transition, the p's would stay as pi. So once you converge to pi, you basically stay there. Is kind of the idea. Okay. Any questions? That's kind of the kind of guarantee that we need. I'm not going to prove that this leads to a stationary distribution, but that's kind of the guarantee. The conditions we need to guarantee that we're going to get a stationary distribution. Yeah.
Is it same as ergodicity property?
Yeah. So this is the homogeneous plus this gives you ergodicity. What's called ergodicity of the Markov chain. Yeah. I think irreducibility is separate, but the aperiodicity plus homogeneous gives you ergodicity. So this is the irreducible and ergodic. Is another way of stating the conditions. Yeah. Okay. Okay. So that's kind of the kind of axioms or kind of conditions we need here. But now I think the thing that really makes this intuitive works in the finite case, why we converge to this stationary distribution, is to think of this in terms of matrices and the p's in terms of vectors, and then consider the eigenanalysis, the spectral analysis of this T matrix. So what we said was this transition matrix basically says if I want P1, now let's think of these P1, Pk, whatever as vectors, right? In this case, like a 3 vector. We said just says take the matrix T and multiply by the previous vector. That gives me the next probability vector. And I can continue this. P2 is just T times P1. So each arrow of the transition is just a matrix multiplication. Okay? And in general, if I'm at the kth stage, I get that probability from the previous k-1 stage again by matrix multiplication. Summarizing all of this, of course, I can just kind of concatenate this is another T and then another T and another T. This is equivalent to just saying if I multiply T to the kth power, P0, then that's how I get to Pk. So really, starting with my initial P0, which I have to specify some initial probability distribution for the very first random variable there, the 0th random variable, I can get to anywhere on the chain I want if I can compute kind of this power of this matrix. I can jump straight ahead to the probability distribution at the kth step. Okay. Now, if I want a stationary distribution, what does that mean? That means that I want it to be the case that applying T to my stationary distribution, I was saying the name stationary comes from. And who can tell me what does that mean about if I think of pi as a vector? What does that mean in terms of matrix lingo?
It's an eigenvector.
Yeah, exactly. So pi is an eigenvector.
Well, don't you need a constant? Well,
Well,
I guess,
yeah, and so it's an eigenvector, and its eigenvalue is what? Is 1, right? So this statement that I want pi to be stationary is equivalent to saying I want t to have an eigenvector, let's call it pi, which has eigenvalue 1. Okay? It turns out that one way to prove that you have a stationary distribution here is through a theorem called the Probabilistic theorem, which, as usual, I'll say refer to the Wikipedia page for the gory details of the theorem. But just to give you the gist of it, the Probabilistic theorem says, in terms, if I satisfy these conditions, and this is a probability matrix of 1, then I'm guaranteed that T matrix will have an eigenvector, a single eigenvector, a unique eigenvector, okay, that has eigenvalue 1. So not only does it have a stationary distribution, that stationary distribution is unique, and the remaining eigenvectors have eigenvalues. They might be complex numbers, the eigenvalues might be complex numbers, but their absolute value is less than 1. And this is an important property. So T will have, let me say, vectors E1, which is equal to this pi stationary distribution, E2 dot 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 out to ED, let's say, and eigenvalues I'm starting to this bad shell here. It has eigenvalues, each of these eigenvectors of lambda 1, which is exactly equal to 1, and then lambda 2, let's say dot 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 down to lambda d, and the absolute value of lambda k is less than 1 for k greater than 1. And so this is like the magnitude of the complex number possibly. Okay? And this is an important property because what it's going to tell us is that this convergence, that this process, I should say, is going to converge to the stationary distribution. So if you think about it, P0, I can decompose it as an eigendecomposition. I can do, this is a basis for my P kind of probability space. I can decompose P0 as a sum of these eigenvectors with some scale factor. And if I take it to the kth power, then each time I do this, it's going to take that vector and shrink each of these components that are 2 through d because they are weighted by something that when I'm basically taking these eigenvalues to a power, and each time I take this to a higher power, it's multiplying a number less than 1 over and over again. And so all of these components shrink away to 0 as I apply this t over and over again. But this component kind of stays put, left with nothing but pi. So no matter what I start with P0, again, it has to be a probability distribution, so it has to sum to 1. No matter what I start with, you apply this enough times, it's going to go to converge to pi. Okay, does everybody follow that kind of eigen argument? Now the other thing that's really a cool trick here with the eigen analysis is that let's say these are in order, so lambda 2 to lambda d are kind of decreasing magnitude order. I also know the convergence of this process. So I can tell you how fast this is going to converge if I know the magnitude 2, you can think of it as a convergence rate. So if this lambda 2, let's say, has absolute value of 0.5, that means each iteration, the magnitude of this component is going to get shrunk in half. So I know my convergence rate is a factor of 1/2. 1/2 to the k is kind of how fast that's vanishing. Okay, so this eigen kind of analysis of this Markov chain process in the finite state case gives us a really kind of strong intuition for this thing has a stationary distribution. Of course, we use for Green's theorem that kind of guarantees that it has a stationary distribution, but then the eigenvalues give us this argument of why it converges and how fast, we know actually how fast it will converge also. Okay, any questions about, I think that's everything. I was going to say, there's one thing I'll throw in here. One sufficient but not necessary condition. So this will guarantee all this works, but you don't have to necessarily have it, is the following condition. So, and it's somewhat easier to check sometimes. As we get into more complicated things like continuous distributions, it's a little bit easier condition to check. We'll see it's important in just a second. But it's this condition called detailed balance. And so if I know the pi distribution that my target, the stationary distribution which is my target, then the detailed balance condition is that is tx, I'll call it tx. And so this is just like a column, for this case it's just like a column and a row column index, x and y are just row column indices, if you will. But I would need t of xy times p of, let's say pi of y is equal to flipping the, I probably should call these jk's, but whatever, you can do the, let's just, flip jk's. In this case, I was doing this because that was, it's going to be continuous values in a minute, but for now, let's just skip the jk's. So I need this to be the case. If I flip the roles of j and k, these are equal. And this is for all possible j's and k's. So this detailed balance condition ends up giving me that I'm going to satisfy everything I need to satisfy to converge to the stationary distribution pi. If you think of this as a conditional probability, this is just saying, really, this is equivalent to just the joint probability of j and k is equal to the joint probability of kj, same thing, is hit the stationary distribution, this joint probability is just the joint of the same probabilities. So this is another condition. It's going to come up, it's more important is when we get to the Metropolis-Hastings algorithm, and more important when we get to continuous, I think, distributions, because here it's it's not so hard to check these properties directly with these small state values. Okay.
This is not necessary condition.
It's not necessary. This condition implies these, but these don't necessarily imply detailed balance. You don't need to have detailed balance. It just turns out to be easier to check for things going forward. We'll see. So we're going to do Metropolis-Hastings, which leads us to Gibbs sampling. And also what we're going to see is called Hamiltonian Monte Carlo. And all of these methods we'll see satisfy, it's easy to show that they satisfy detailed balance, and that's how we'll verify that they work. And what the point of detailed balance here is satisfying these conditions what the pi is, right? And so if I already know pi, because typically, remember, our goal is to get pi, and so we start with pi. That's our goal. And so in order to see if we get the distribution we think we're going to get, you can kind of check this detailed balance, because you know pi, that's the target distribution in most MCMC cases. And then you kind of check with whatever transition you're using, does it satisfy this detail balance? Which that's kind of the idea. Okay. Any other questions? Okay. Okay, so the first question is, how do we generalize this to more complicated cases, and specifically, how do we generalize this to the continuous case? So in the continuous case, we don't have kind of this matrix per se, but what we can do is say the xk's are continuous, which, really just mean, let's just say real value, real numbers. Then we're going to replace the transition matrix with a transition kernel. And I'm going to call this K for kernel, just to distinguish it from T. You could also call it T, but it's a different type of object. It's just, again, just defined as the arrows. It's just the conditional distribution that you get from the arrows. So I'm really going to call this, I'll write it this way, that the random variable xk and xk minus 1, the transition kernel is just the conditional probability of xk given a particular value here for xk minus 1, right? And this, of course, is a continuous function specifying this xk minus, or it's probably, it's going to be continuous, I should say. This is a probably density, we should say. So this is a real value PDF, right? So it's not a matrix per se, but really, if I let both of these be variables, it's like a multivariate function. This kernel is one way to think of this. Is it's a bivariate function. If I let xk and xk minus 1 both be any real thing, okay? And now, how do I transition? So over here, I transition from k minus 1 to k by a matrix multiplication. Of course, I don't have matrix multiplication in this case, but what we're going to do is just say we're using the usual probability rule is that p of xk is just the marginal of the joint distribution of xk and xk minus 1 integrated over xk minus 1. Right? And because I know this transition kernel k is this conditional distribution, I can write the joint down as probability of xk minus 1 times xk given xk minus 1, again integrated over xk minus 1. And this is just what I'm calling the k transition kernel. And so this thing really just looks like always an integral of my transition kernel times my previous PMF, PDF in this case, for xk minus 1. I guess to have been consistent, I probably should put, this is a different PDF. This is the marginal for xk, right? And this is the marginal for xk minus 1. So I want to be clear that these are different PDFs. I could probably put a subscript there, but it's also clear, hopefully, from the context of what's inside the parentheses, but just to be extra clear here. Okay, so now our step looks like you take, to get to the xk PDF, you do this multiplication followed by integration. This is basically the continuous version of matrix multiplication. And so if you think about this is a linear operator. This is basically, first of all, if you know convolution, this is kind of a convolution. So this K is like a kernel that we're convolving against, where K minus 1 is the variable we're convolving over here. And so you can think of this as a convolution by some kind of kernel. And it's also a linear operator, right? Because if I think of integration, it's linear in the thing I'm applying it to. So these P's are like vectors now, or like the vectors we have here, and this operation that we're doing here really is equivalent in the continuous case of a matrix multiplication, the linear operator. So if you know anything about infinite dimensional vector spaces, this is just a linear operation on the Hilbert space, and so forth. So it really is just the infinite dimensional version of this matrix operation here. Okay, and these infinite dimensional kernels here also can have eigenvectors and eigenvalues, and a very similar, at least in spirit, kind of argument tells you that if you again satisfy, now you have to have a slightly different condition than aperiodicity, and the irreducibility and aperiodicity are a little because you have to say, you never can get exactly to a state because it's continuous. You have probably zero of any exact state, but basically any area, like any kind of area I would give you, you have to have non-zero probability that you would venture into that area, basically, is the idea. And you don't get kind of stuck places. Anyway, that's a paraphrasing of the continuous version of these properties. But again, an easier thing to check than really the veridicity of this transition kernel is, again, detailed balance. And so the detailed balance condition here is in terms of the K kernel. It's the same kind of thing I wrote earlier with the T, but it's anytime I give I should say this is our actually call this pi again. So again, we have a stationary distribution pi, and for it to be the stationary distribution that this process is going to converge to, I need this same condition to hold that we talked about there. So x and y are now continuous values, and this is really just this is just a bivariate function. It has to be equivalent to a PDF. But this is just a bivariate function. This is just a univariate function. It's a PDF, and that this multiplication has to be oops, I got this backwards. Has to equal this multiplication. And again, this is just the conditional x given y times p of y has to equal the conditional p of y given x times p of x. And that's just showing that no matter which way I do this, I get the same joint. Okay. So anyway, this this process is, it's resorting to infinite dimensional vector spaces and arguments about kernels and things like that, but it's not really necessary, I think, to know kind of that infinite dimensional math to get the intuition for what's going on. I think that's the finite version of things gives you the intuition for why these things converge to work the way they do. You don't have to be an expert in functional analysis and Hilbert space theory to necessarily things and understand, at least at an intuitive level, why they work. Okay. Any questions so far? Okay. Right. So let me just give a quick example of a continuous Markov chain. So there is the very simplest, at least that I can think of, non-trivial, I should say, example of a Markov chain is progressive, and we'll just use the notation AR for autoregressive, and then this is the order of the autoregressive is order 1, which just means in this case that autoregressive 1 we're going to see makes this a Markov chain that is only one. We like to look one step back to get conditional distribution. If you have autoregressive of a higher order, it looks further back, and then it kind of remembers states further back than just one. So that's why we stick with one. And the way this is defined is I'll start off with x0 just being the Gaussian mean 0 and some sigma square variance. And then basically this is my transition kernel. Xk is equal to xk minus 1 plus some noise. And that noise is also Gaussian 0 mean variance sigma squared. Oh wait, sorry. I can multiply this by theta. So theta is constant. Let's make theta should be less than 1. Theta less than 1 greater than 0. So theta is something in between 0 and 1.
The standard deviation should be different.
No, well, I'm going to make this variance equal all the way throughout.
2x now?
Well, okay, I could make this anything really technically, yeah. But since this is my transition, I mean, I'm just doing that to be consistent. Is typically what we would do. But you're right. I mean, I can actually set x naught to anything we want. But I'm just going to start it with. I can start x0 equals 0, like as a constant or something like that. But, yeah, I mean, we'll just keep it consistent there. And that's kind of defining my transition probability, right? So I need to keep this distribution fixed. And theta needs to be a constant. I can't change it halfway through the process either. So it's got to kind of, this has to stay fixed. I can do, yeah, I think 0 is important for it to be 0 mean, but I can do, I do have to keep the sigma squared constant. Yeah, but I can do whatever variance you want. Okay. So what's going on here? So if I didn't have this piece here, we would just have IID Gaussian sample, right? I just have, so this piece here, theta times xk minus 1 basically says take the previous x, multiply it by some scale factor, and then add noise on top of it. As you can see, there's a clear dependency with the previous random variable. And of course, if I go back to xk minus 2, that had some influence on xk, but if I know xk minus 1, I don't need to know anything before it because that tells me exactly the conditional distribution of xk is just, I mean, really I could say, well, another way to say this is that xk given xk minus 1, this conditional distribution is just Gaussian with mean theta xk minus 1 variance sigma squared. There's another way to write this AR model. Okay. So this is the transition kernel, this K. The conditional distribution is this Gaussian PDF. Right. And if I think of it as a function of xk minus 1 in xk, that PDF is really a two-dimensional function if you think of it that way. You typically would think of this is fixed and then there's a PDF just of that. If I want to think of this as a K kernel, as a two-dimensional function, then I can do that as well. Okay. So anyway, that's have called autoregressive order 1 on this. And it comes up in time series analysis, and particularly in analysis of noise processes in time series where there's correlation in the noise. So if you think of a time series and somehow the noise you're getting is not completely independent but actually it was dependent on the previous points. There's some correlation effect in the noise. That is the regressive models very often good models for that. Just a couple points about some properties here. I'll do a quick code example,
Does this also apply when you have like iterative algorithms and you have error induced in each iteration?
Can you?
Do you want to look this way?
I mean, I assume so. I can't think of a. If I'm trying to think, if I have a. I guess so. If you knew your noise or your error was always, if you model, if the safety model always is Gaussian, then yeah, that's exactly the kind of process that would. So if you had iterative algorithm, the error in your computation, they had some little epsilon added to it. And there's probably a central limit theorem argument that it doesn't have to be exactly Gaussian, but yeah, then that probably would be, that would make sense to model this way. Okay, so what's the stationary distribution here? So the stationary distribution pi of x is just Gaussian in the end with some mean and some variance tau squared. Okay. And one way to kind of see that argument is that if you think about scaling a Gaussian and adding another Gaussian, you just always get Gaussian, right? And so actually all the x's are Gaussian. And so in the limit, if I converge to something, it's got to be Gaussian. It's easy to show, maybe, this is, I'll leave this maybe as an exercise yourself. Think about why does this satisfy detailed balance, this visual distribution. Okay, so think about that, and hopefully that should be not too difficult to show. About it carefully. It's a little bit tricky to think about it carefully. But then a quick argument for what is mu. If you think about taking the expected value of xk, that's mu, right? The expected value of xk, this has expected value of 0. This has expected value of theta times the expected value of the previous one. And if I've hit my stationary distribution, that means that the expected value of pi, if x is already from the pi distribution, and this is from the pi distribution, that means that mu has to equal theta times mu. Theta is non-zero, so the only way I can get is if mu is what? There's only one value for mu that will satisfy this equation for theta being something between 0 and 1. How can mu be 1/2 mu, for instance? Yeah, mu 0. Okay, so mu has to be 0 for, because again, theta, because if theta was 0, then I think any mu would work. But, then only mu 0. Anyway, the point is, yeah, this is non-zero. Mu has to be 0. Okay? And then similarly, if I take the variance of both sides of this equation, I've got the, and this is in the stationary distribution, these are to help converge to the stationary distribution. The variance, which is tau squared, has to equal, remember variance works that these are independent because epsilon is just independent by itself. So this has variance sigma squared. This has variance tau squared. If I pull the theta out, it gets squared. So I get the relationships that tau squared has to equal theta squared, tau squared plus sigma squared. Okay, and this not degenerate to, do you have a question yet?
So this.
Yeah, I'm just
theta
taking,
2 plus 0.
yeah, I'm just taking the variance of both sides of that equation. Yeah, they have, yeah. And so now if I solve for tau, this equation looks like, let's see, sigma squared over 1 minus theta squared. And you can see why I kind of capped theta at 1, strictly less than 1, because if I get up to 1, this gives me infinite variance, and the thing blows up and does not converge to a stationary distribution. Okay. AR is a complicated MCMC method you can think of to generate a Gaussian distribution. That's not what we would use it for usually. But this is just an example of a continuous distribution that's probably the simplest case that we can analyze exactly what it does, how it behaves, in terms of its stationary distribution and so forth. Okay. Any questions? All right. Let's see, I have a code example, but maybe I've got time to squeeze, which is kind of the goal of all this anyway. So let's try to at least squeeze in the definition of Metropolis-Hastings here. Yeah, okay. So if you read the paper that's the reading for this week, or I mean, really since Thursday, I guess, the Andrew paper, in the introduction they talk about Metropolis-Hastings, like there was some kind of list of top 10 computer science algorithms of all time or something, and Metropolis-Hastings was, in that list. So Metropolis-Hastings is really one of the probably most famous and most important computer science, I guess there's not non-computer science algorithms, the most important algorithms that we've had. And all of the kind of applications of that we've talked about of Monte Carlo method really became possible with this idea of Metropolis algorithm, which basically makes this possible. That makes this converging to a stationary distribution that is your goal distribution possible, and it really opened up our ability to sample from almost any distribution you can imagine. And led to this kind of whole class of algorithms that we're going to talk about today and next time. And so yeah, so it is a really critical algorithm, and with computing power, it's actually feasible now. We can actually, it's actually practically useful. Okay, so how does Metropolis-Hastings work? And we talked about, if you remember last week, acceptance rejection. Sampler, and there we had to have a proposal distribution, which was kind of our guess for the distribution we wanted, that we couldn't sample from directly, but we gave a simpler distribution, let's call it g of x, that we sampled from instead, and we wanted to make it as close to the distribution we wanted as possible, bounded by some constant c, and then we had this decision rule, this acceptance probability of either accepting or rejecting that proposal sample that we would get. And we saw that led to, through a probability argument, the probability for the accepted samples had the right distribution. So the Metropolis-Hastings algorithm is actually very, very similar. It is an acceptance rejection method. But the difference is, instead of just having a fixed proposal distribution for g of x, we're going to have instead this whole setup that we've talked about, it's a conditional distribution. And I can actually start with x0 being just about any kind of random value generated however I want. And then I just really need a conditional distribution to be some we're going to see proposal transition. Okay, and basically that's kind of the story. So the details are, again, I'm going to have a proposal and it is we'll call it g of y given x. So I just defined some proposal conditional density. I should mention, okay, let's just kind of set what we want is we some PDF. Let's call it pi of x in the end. That's what we want to sample from. Is some distribution pi of x. I'm going to just use pi, the same as the stationary distribution, because we're going to see it is a stationary density for this process, this metropolis-Hastings process. Okay, and so the steps are, you know, I first start with x0, just initialize somehow. So, you know, take a random Gaussian or whatever you want to do, if it's continuous or some random discrete. Just initialize x0 by some way. Okay. And then you iterate the following. So generate, so this is like our k iteration in the chain. I'm going to generate a proposal, let's call it y, is going to be sampled, so let's say sample y. I'm going to put some numbers here for the steps here. Sample y from the proposal, y given our previous xk minus 1 value that we sampled. So this is, I've already generated up to xk minus 1. I'm trying to generate sk here. So sample y from the proposal. And just like in acceptance rejection, I'm going to also sample a uniform, u. This is going to be the thing that, just like I remember in acceptance rejection, this is the thing that I'm going to have a condition to test. It's going to be whether I accept or reject this proposal sample. Then the accept reject condition is I'm going to check is u less than or equal, less than or equal or less than, doesn't matter, to pi of y times g of xk minus 1 y divided by pi of xk minus 1 g of y given xk minus 1. Okay? And if so, if you know this checks, then accept your xk equal to y if that condition holds. Otherwise, and this is kind of the this is an important trick here. When we reject, it doesn't mean you throw away that sample. Okay, so this is a little bit. So this messes people up sometimes when you actually implement these algorithms. You shouldn't throw away. Rejection does not mean throw away. What it means is that you actually use the previous sample as the new sample. So you just repeat the previous sample. So when you reject, you're still getting a sample. It's not a very useful sample, it turns out, but it should still be included. So you can get stuck for a little while if you reject several in a row. You can get stuck with the same value, but that's what you're supposed to do. You're supposed to keep repeating that sample every time you reject. Okay? Yeah, question.
And that's because of detailed balance, right? This ratio is somehow from detailed balance.
Yes, it is because,
If
yeah, it is
gets-
because
it's saying it's getting worse. That ratio, if it, like, if numerator is,
well, so yeah, so the we're going to see it is because of detailed balance. It's not completely obvious, I think, why, but And maybe you see why, in a straightforward way that I'm not seeing.
I'm not 100% clear. There is some connection.
But yeah, but you're absolutely right. It is because of detail balance. And yeah, yeah, that's a good question. There's a simple intuition of it. Oh, I think I'm missing. Sorry, I'm missing something. This. Well, actually, it doesn't matter. Usually, this like you look at the entry paper. This is the minimum of this one. But yeah, that doesn't matter because if this is 1 greater than 1 and then 1, then this is always true. So yeah, that doesn't matter. Yes, this is fine. So you'll see in the entry paper, I just looked at that paper, the algorithm box there, they have a minimum of this and 1, but I think that really doesn't, if I'm thinking this correctly, does not make a difference. That shouldn't matter.
It's bigger than 1.
And 1 will come from the right?
Yeah, the 1 is important in the argument of detail balance. So if you read in there in the paper about the detail balance argument, then the 1 does it is important to some extent. But basically, because you have to call this a probability. For the detail balance argument, this has to be a probability, so you have to cap it at 1. So if it goes over 1, you clamp it at 1, so it's still a probability, and the detail balance argument still holds. Okay. Okay, yeah, I don't have time. Read the detail balance argument, but I really want to show the code and then just preview the. So I've given you the Metropolis Hastings algorithm, and I'm just going to leave as a thing hanging that this actually works. Yeah, question. Okay, I'll go first.
Check.
Yeah.
We can look at the denominator as the probability to transition from x k minus 1 to y.
Yeah. Yeah, this is the probability that we're going to transition right to
y to numerator is from go from y to x k minus 1. The denominator is like k minus 1 to y. And
Right.
if the denominator is larger, which means you can go from x k minus 1 to y and therefore keep x k minus 1.
If the numerator is large, if the denominator is larger, then you have a lower chance of accepting. Yeah. So
So you accept if the bottom is large, right? If that's close to 0, then the chance that you would be larger. Oh.
No. If the denominator is large, I'm going to reject more. Think of probability of accepting, right? So the denominator is large relative to the numerator, the probability of accepting is lower. Okay,
When
so
do you stop iterating?
No, but there is still u which is randomly sampled from 0 to 1.
right.
Right?
At this
So
point,
if the denominator is larger, still we do not say the probability of acceptance is lower.
Well, we're not accepting this as a value of pi of x, we're just accepting it as the next value of the iteration, right?
Yeah, this is xk, right, which is not from pi. It's not from the pi distribution. So xk is you know, it will come from pi.
So when do we stop?
Okay, so we're going to get into when we stop. Okay, so right, so well, first of all, there's a couple things. When do I stop? Okay, so remember we're trying to do Monte Carlo, meaning we're generating a random sample from, we hope, the pi distribution, such that the expected value that we're looking for is approximated. Remember, the Monte Carlo method, we're always. Okay, I probably should have just gone to the code and not wrote some methods because I can't. Yeah, so we'll run out of time, but let's just keep discussing and see what we get come up with. Okay, so remember Monte Carlo, what are we doing? We're trying to value of g of x, where G is just some function now, not this proposal thing. This is just any function you want. It doesn't have to be P or anything. Just some function of a random variable x. X is from this pi distribution that we don't know how to directly sample from. And we approximate this, remember, by taking m samples and taking their average. So the xk's all came from this Markov chain. Now there's a couple things when we get to MCA that are important here. This Monte Carlo method that we talked about, first of all, we talked about the strong law of large numbers and essential limit theorem, that this all was guaranteed to work, yada yada. But that was because we were assuming we were actually sampling from the right distribution of x. We were sampling from the pi distribution. And that the samples were IID. That's a condition in the strong law of large numbers and the central limit theorem. Now, we don't have that anymore. We have a Markov chain, and the xi's or xk's I'm sampling are not independent. So we broke the IID. And they're not even from the right pi distribution, so we really broke. They're not identical or independent, and they're not even the right distribution. So now we need, I forgot, we need to revisit our whole goal here of Monte Carlo is to get these expectations. And it turns out that there is a generalized version of the strong law of large numbers. So if you remember, the strong law of large numbers says this converges almost surely, meaning with probability 1 of the limit as m goes to infinity. It turns out that there's a strong law of large numbers that also works if the xk are from a Markov chain that converges to pi. That our strong law of large numbers still holds. So as xk's converge to pi, m goes to infinity, this converges with probability 1 to the thing we want. So we're safe, that there's theory behind it that this will still work. Now in practice, so getting to your question about when do we stop, there's actually two questions. When do we start and when do we stop? So what I mean by that is you initialize x to some arbitrary value that might be really a horrible, not at all a plausible sample from pi. And it turns out that you should, before you even start recording samples and putting them into your expectation plot. So there's a phase called burn-in. And in burn-in, it basically means run your Markov chain for a while, but don't save anything. Just keep throwing away the xk's. I mean, you have to keep the previous one to get the next one, but don't use them yet. And so you run for some time, and that lets you do two things. It lets you get rid of a bad initialization, and it lets you start to converge towards this stable stationary distribution pi. Pi, which you don't know whether you converge or not, there's no way to know how much burn-in is enough burn-in. Meaning there's no theoretical guarantee of how long you should burn in. And then second, when do I stop is the same question in Monte Carlo. You have the same kind of convergence rate properties of roughly, and again, this is trickier because they're correlated, but if your sampler is exploring space well enough, you can actually get roughly the same square root n convergence. I've got it in my code example, which is, oh wait, no. Anyway, I think I'll post it for next time, actually. The chocolate tasting code I haven't posted yet, but the Markov chain I have posted. Anyway, we'll see. I'll get to that on Thursday. Yeah, let me save that till Thursday. But let me give just the general way that you can evaluate have I converged to my stationary distribution or not. And one general principle, and this is kind of I'll give kind of the intuition here, is to run multiple chains. Okay, so if I run just one of these chains, it can be kind of difficult to see whether it's converged to something or not. But if I run parallel chains and they all randomly initialize differently, then technically they'd be initialized the same way because you do randomly, the steps are all random and different. But anyway, I run parallel chains then I look at now, instead of just one sample at a time, I look at kind of each chain jointly together and see, are they looking like they're coming from the same distribution over some stretch of time. And so there's a statistic that we'll talk about just briefly on Thursday that kind of looks at these parallel chains and says, you know, you can basically think of like, how would I see if they're the same distribution or not? I can do all sorts of different things, but very simple things I can do are do they have the same needs, do they have the same variances, the parallel chains I'm running, and they look like they're giving me the same kind of random variables, and that's an indication that I've gotten some kind of stationary, I've gone long enough to get a stationary distribution. So that's kind of the intuition for how to check this. Okay, so yeah, so you have to burn in, and then how long you go depends on, again, the accuracy you want in whatever expected value that you're trying to compute. Yeah.
How do we make sure it converges to the pi that we want? So how do we specify the initialization? Would it be not in MCMC or the
Yeah, so a lot of this is, I'll say, the black magic of, as you will all learn over the next couple of weeks, the black magic of MCMC methods. And one of the reasons why you know, some people really don't like them is that there's really, I think, no way to know to guarantee, and there's not really a way. So when you do like your Gibbs sampler that you're going to do with the homework, and you're sampling images basically each time, dimensional thing, you will not know if it's the right distribution or not. But what you'll know from that is what you want the algorithm to do is to sample a posterior which looks like a clean image from a noisy image, and you'll know just qualitatively, oh, it seems to be working. So for the homework, don't worry, it won't be, you'll know whether it's working or not. It's not that bad, but yeah, it really is a black, you know, art and we're going to see these MCMC algorithms like the Gibbs sampler and the HMC, Hamiltonian Monte Carlo, typically you have things like the proposal, the G proposal distribution. You have to kind of set this all up and tune it and make it work, and it's not always easy to do. So I can't give you like, this is a rule of how you always should do this, because this is a very, very general algorithm. Depending how you set G and how you, basically, yeah, how you set G, this is actually a whole family of algorithms. And there's no one way to say this will definitely work if you do exactly this initialization and exactly this check to see if it converges and all that kind of thing. But we're going to kind of see some heuristics and some basic rules, best practice, let's call it, that this you know, tends to work. Yeah, question.
How do we verify that how to choose this G function?
Yeah, again,
What
that's.
this G function is going to be.
Yeah, I really shouldn't have introduced this at the end of a class because we're out of time. So yeah, so how do I choose the G function? Again, there's no rule that always works for how to choose G. But I'll get into that more on Thursday because there's a lot of considerations there, and it actually lead to multiple algorithms. We'll see.
It's not a probability distribution.
No, this is a probabilistic PDF. Yeah. That I'm sampling, that I know how to sample from. So the first thing, there's a couple things. I have to choose something that I know how to sample from. That's the obvious thing, because this step wouldn't be possible otherwise. The second thing, and we'll get into this in more detail, let me just give you kind of the gist of it. I want this to have high probability in places where I want to sample like pi. So for instance, I need to somehow explore the areas that have probability in my pi distribution. So choosing G in a way that will give me exploration in the right places is the thing.
And so I can always make sure I have probability. If I'm in a place of high probability, if I make G like a very narrow, tight, like Gaussian, let's say, and take very tiny steps here, it's like a random, we'll see there's a random walk, it looks like a random walk, then I'm guaranteed this will stay kind of high probability. But if I won't go very far, and I'll miss places that, so there's a trade-off between taking small steps and accepting a lot if you get in a nice high probability spot, but then you don't explore the whole distribution. So there's a trade-off between large exploration, which tends to reject a lot, and very little exploration, but you tend to accept a lot. And we'll kind of discuss that balance and how to make that work starting Thursday, I think. Okay, so I'm over time. Look at the code online. We'll start off class on Thursday with it, but it just goes through some examples of these Markov chains and some of this eigenvalue stuff, and it does the AR model as an example and sees how it just prints out how it's converging as you kind of see this stuff in action. But we'll start Thursday with the code example.